So we're switching gears entirely from deposit atlases and coming back to rare earths. And in the schedule, you would have seen that the next session is called Rare Earth Grades 101. And really the aim of it was to just talk about some aspects of rare earths, the rare earth market, and processing. And oh, I better share my screen here. That's going to help. Oh, my screen's shared. I just have to put something in it. Right. So this is going to be, even though there are extra names that didn't appear in the schedule, and so Lisette Verster will be. Well, actually, I'll just go ahead to the outline. So this is what we're going to talk about. I'm going to talk a little bit about rare earth markets and a very high level look at the relative value of different rare earths and what's driving them and that sort of thing. And I'm sure that some of you have seen a lot of this already, so we won't spend too much time on that. And then I've asked a couple of participants from our rare earth processing project, both metallurgists, Lisette Verster, who's from the Julius Kruschnitt Mineral Research Center, who's an expert in flotation, pre-concentration, and James Vaughan from the UQ Chemical Engineering, who's an expert in hydrometallurgy, to talk about some of the processes around rare earth processing. And again, I've asked them both to keep it at a pretty basic level. So those of you who are experts in rare earth pre-concentration hydrometallurgy will, you might find it a little basic, but I suspected that there would be quite a few people here who weren't experts in rare earth pre-concentration and hydrometallurgy, and I knew of at least one at the podium, so I thought that'd be all right. And then Paul was going to do a little bit of an update on where we're at with our rare earth project. We've just published a paper on the Mary Kathleen tailings, so that'll probably get touched on. And then the last half hour of the session will be over to Dave Houston from Geoscience Australia to talk about the economic value of critical metals and some of the work that Geoscience Australia is doing. And then we've got a little bit of an exercise, and some Excel spreadsheets have been handed out along with that, that will allow you to also do a bit of hands-on work looking at the relative value of critical minerals in an analysis. So the first thing I want to do is, I'm sure that some of you have been watching the Ore Deposits Hub. And the very first thing I want to do, and I think I'd be remiss if I didn't because I stole about 4 of his slides, I think, would be to talk about Darren Smith's presentation from the Ore Deposits Hub. If you haven't seen this and you're interested in rare earths from a pragmatic point of view, it's well worth looking at. So there's lots of presentations in various different types where people from more of an academic background have said, look, I found a rare earth mineral in this rock, therefore it has great economic implications, and I've done this over here, or I've found 0.0001% such and such lanthanum or something, and that's really significant and it's going to save the world. This is a presentation that actually talks very pragmatically about what characterizes the deposits that are actually in production now and what they have to achieve to be in production. I'm not saying therefore lose all hope if they don't match what's being described now, because it's an item, there's a lot of research going on to find ways to treat other types of rare earth deposits, including research by us that Paul's going to talk about, but it is a really good introduction to the market and some of the processing. This isn't from that presentation, though. It's from another presentation that came out in the last little while. And it basically talks more about critical minerals and basically presents a lot of the information that probably a lot of you are fairly familiar with, and that is that the situation where we as a group have found ourselves a little bit behind the 8 ball when it comes to supply of critical minerals, particularly rare earths. because we're very much at the focused at the source end of things. There are very few integrated operations in the West, and we're very beholden to China that has been developing an integrated rare earth industry for quite a while. And of course, the reason that we're interested, and this is from the Achieving the Paris Agreement Goals publication of 2019, when you look at the elements required for wind power, neodymium, dysprosium are up there. The ones with the stars against them are all rare earths. Battery elements, of course, and we're going to spend a bit more time talking about that. But again, neodymium, dysprosium come out very well. If you look at, and this is some work done by Martin Stringer, who's currently with the BRC as well, but was formerly with the Dow Center. If you look at this was an analysis that looked at all of a whole range of different commodities that were going to be required in order for us to meet our current Paris climate goals. And basically, then it's actually a routine. I'm not going to run the routine, but it's a routine that runs and shows you what happens if any of those things are missing, the extent to which that's going to jeopardize us missing our climate goals. And you can see that there are four, there are four rare earth elements on there, and this is the first time that group of four appears, but it's going to appear again in this talk a few times: neodymium, dysprosium, praseodymium, and terbium. Now, one of the interesting things, and this is one from Darren Smith's talk, is it's something that I hadn't really realized, and that is that when you look at the crustal abundance of rare earth elements, they're quite abundant. Cerium is more abundant than copper, and neodymium, praseodymium, and yttrium are more abundant than lead. The problem is that when you find copper, it's usually sitting in minerals that have got a lot of copper in them. And when you find lead, it's sitting in minerals that have got a lot of lead in them. But a lot of the rare earths are sitting in minerals with not much rare earths in them. So it's very much harder to get them into a form that you can actually economically treat and separate the rare earths. And that's probably, that plus demand is probably one of the reasons that in 2019 we produced about 3 orders of magnitude more copper than we did rare earths. Here's another really interesting thing, and again, it's taken from Adamas Intelligence. They've done a really good report on this. Unfortunately, it cost several $1,000s, so instead I stole this from various free sites, but it's something that looks, so the left-hand diagram here is looking at, it might be a little bit hard to read that, but looking at categories of uses for different rare earth minerals, and there are battery alloys, catalysts, ceramics, pigments, glass polishing, metallurgy and alloys, magnets, phosphors, etc. And then by volume, what you can see is that catalysts become more important, permanent magnets become more important, glass polishing. And then when you look at value, that's all magnets. So it's magnets, basically. That's another one of and basically neodymium, praseodymium are what are really essential for magnets. And dysprosium and terbium make the magnets work at higher temperature. So they're very expensive because they're much more rare, but they're also more, because of that, they're more susceptible to substitution. So, but if they're not present in some way, you have to find some other way to make the magnet stable at high temperature. So the other thing in there is that basically the forecast from Adamas Intelligence is 9% annual gain in value from 2020 to 2030 for those main 4 magnet feed minerals or elements. And a large amount of the driving of that, this is from an Arafura corporate presentation, but the big mouth here is electric vehicles coming out to, you probably can't see that, but that's 2030. So it's basically just looking at uses of the demand, in this case for neodymium iron boron magnets. Everything else is staying the same. So, that's other, according to this analysis anyway, air conditioning is growing a little bit. Consumer electronics is moving around a little bit, but electric vehicles and traction motors for electric vehicles are the big growth. And here's another way to look at it. In this case, the black lines here are neodymium, praseodymium magnet tons as of 2016, and then again the forecast compound annual growth rate. That's what CAGR stands for. I had to look it up. I'm sure you all knew, but and just different things. So the compound annual growth rate for automotive is 10%. Electric vehicles more like 12, and so on. Battery electric vehicles 30. Air conditioning, I suppose global warming and so on. Hard disks are, I wouldn't invest in hard disks if I were you, but because they have no forecast growth whatsoever. But again, it sort of emphasizes that trend. And what that leads to is a bit of a balance problem. So when you look at differing markets, basically, as we've heard already, most deposits come with a cocktail of rare earth elements. They come together. And what that essentially leads to is an undersupply of the stuff we want, which is neodymium, praseodymium, and so on, and an oversupply of things like lanthanum and cerium. So one thing that you shouldn't do when you calculate the value of your ore is load it up with the value of lanthanum and cerium, because no one's going to want to buy it probably. And the forecast price trends are shown, if I can get my mouse over there, down here. The two big high lines here again are praseodymium, neodymium, and then gadolinium, terbium, dysprosium, holmium, yttrium. Everything else is forecast to go down. And this is a point a few people have made as well. So the rare earth content of certain common rare earth minerals, so bastnäsite, monazite, xenotime, and I don't really know much about loparite, but they basically, this shows their rare earth oxide content, so they're relatively high in rare earths, and so are susceptible to concentration. So that's one of the challenges, of course, is if your deposit's full of eudialyte, you're never going to be able to concentrate it past about 8%. If you do a mineral concentrate, you have to find some other way to deal with it. And the other point there is that when you look at most of the operating deposits now, they actually achieve a concentrate of between 30 and 75% before they actually start treating it chemically. So, but saying anything more about that would be stealing the thunder of the metallurgists who actually know what they're talking about. So I won't say anything more on that front, other than to say rare earths are abundant in the crust, not in concentrated form. Magnets really dominate their value, and it's quite strongly linked to projected electric vehicle growth. And the 4 battery rare earths are really the ones that are going to drive demand, and co-production of lanthanum and cerium and other less desirable rare earth elements is going to exceed demand. And as we'll see in a second, the mineralogy is very important. Metallurgy is relatively complex.